Alright, hi everybody. So last time I had a little bit of weird echo with the audio, so hopefully that's fixed. So I just wanted to go through, so you guys filled out that Google form while you were watching it, and now I just kind of want to talk about what we saw and what we noticed and analyze that and try to fit that in with our prior learning. So we saw, okay, what did the ice skater do to speed up? So in our video we saw, okay, well she moved her leg in to speed up. Before, let's see if I can pull that up really quick again. Before her leg was far out, man. And then, come on. Then she brings that leg in, closer to her body, closer to that central axis of rotation, and she goes really, really fast. So we're looking at, okay, well her leg was far away, and then it moved closer. And if we're thinking about what variable that is, we talked about when we did like that tightrope walking lab, we talked about the idea that we have this rotational inertia that's based on the mass of an object and then where that mass is located. So you guys in that lab, you said, okay, if our mass is really far away, then it's going to be harder to angularly accelerate, harder to spin. And we said if we have more mass that's far away, it is also harder to spin. So we saw that in our real life lab before we left, when we were doing the tightrope thing. And now we're seeing that idea show up again, but in a different form. So we saw, okay, we changed the rotational inertia. She changed how the mass of her body was distributed in relation to that central axis. So when she kind of changed her radius, I guess is one way to think about it, she decreased that radius, like where her mass was located. If we're looking, sorry, I don't know if you can see where my cursor is. We're looking at like maybe a hoop or some other object. She's really changing, hey, where is her mass located in relation to this central axis? And we saw, okay, well, she brought her mass closer, which also decreased our I. We decreased our moment of inertia. Her moment of inertia decreased. And what we saw was when her moment of inertia decreased because of that distribution of the mass, when that decreased, we saw she began to move quicker. She began to spin faster. And I don't know where that question is. I guess it got cut off, but that's okay. So we saw, okay, well, as her I decreased, that moment of inertia decreased, her angular velocity went up. So her angular velocity, her rate of spinning, went up. We saw she got up to, what, 308 rotations per minute? So times, what, 2 pi, some amount of radians per second. Her angular speed went up. That shot up. So when I went down, angular speed went up. And then what do we change about the Hoberman sphere? It's really the same thing. First we had this sphere that was kind of, far away. All the mass was more on this outer edge. And then that man pulled the rope, and that mass kind of changed its distribution. The mass got closer to our central axis, and that's pretty much the same exact case. We saw our moment of inertia went down, so our angular velocity went up. What we're going to see in the next video is why that happened, and we're going to relate it to what we've seen before. So before you go to the next video, start thinking about what is our linear analog to rotational inertia. What's our linear analog to rotational velocity, and have we had any relationship between those two before? Like the old rotational inertia, our linear angular, that doesn't make any sense. What we talked about, what is I related to, and then what's our omega related to, our rotational velocity. So I'll see you in the next video.